How's it going, ladies and gentlemen? Mr. Donnie here again. Today we're going to look at colligative properties. What are they, and why do they matter? So in this video, we'll talk about what is a colligative property. We'll get the definition. We'll talk about electrolytes versus non-electrolytes and why they matter. We'll talk about vapor pressure depression, and I have an analogy for you where it's basically the solute holds on to the molecules and prevents vaporization. It'll make more sense after I have some images. Boiling point elevation, I have another analogy where the solute holds on to the molecules, so you need more energy to boil, which is why you got to get the temperature up. And freezing point depression, an analogy being the solute gets in the way of becoming nice and neat, like in the solid phase. So it needs to get even colder in order to get that nice and neat arrangement. So first question is, well, what is a colligative property? Simple definition of a colligative property is a physical property of a solution that depends on how much stuff is dissolved. So if it changes depending on how much stuff is dissolved, it's a colligative property. So first we need to consider, is our solute an electrolyte or a non-electrolyte? Now you may be asking, well, what the heck is an electrolyte? An electrolyte is something that when it dissolves in water, it will conduct electricity. So if we take a look at NaCl, when it dissolves, it breaks up into Na plus and Cl minus ions. So that is an electrolyte. It's going to produce ions that are able to move around, so it'll conduct electricity. Whereas CO2 will not. CO2 is just going to stay as a CO2 molecule. It's not going to break apart. It's going to stay together, so it's a non-electrolyte. So a number of particles. So let's take a look, because if colligative property depends on how much stuff there is, we got to talk about, well, how much stuff does it break apart into? So for example, we got MgCl2. Well, MgCl2 is going to break up into an Mg plus and 2 Cl minus ions. So we will get 3 particles from MgCl2. Now if we take a look at Na3PO4, we're going to get 3 Na pluses. And now what's going to throw you off is this PO4. That's a polyatomic ion. The PO4 is going to stick together as just one ion. It's going to be 1 PO4 minus 3 ion. So here we would get 4 ions from that. So vapor pressure, it's hard to say that 5 times. Vapor pressure depression, vapor pressure depression, vapor pressure depression. So we got a flask here that's sealed off, and some of these gas particles are going to vaporize and go into the gas phase and cause some pressure inside of that container. Call that vapor pressure. So now what would happen if we, hey, let me throw in some solute particles. All right, oh, too far. So now I got some solute particles in the solution, and they're going to form an attraction between those molecules, right? Because of the solute-solvent interactions, there's going to be an attraction between the solute particles in the water. So now let's think about this. If there's an attraction between the water and the particles in there, well, those particles are kind of pulling them back into the liquid phase. They're like, hey, where are you going, man? Hey, you right there. Where you going? You gonna leave me? Don't leave me. I thought we were friends. And then this guy's like, fine, all right, I'll hang out. So what happens to the amount of stuff that's going into the vapor phase is it decreases. It doesn't happen as much. So we're not going to get as much pressure inside of the container because the solute is going to, hey man, where you going? Don't leave me. So the vapor pressure goes down. Similar thing happens with boiling point. You got these particles that are in there, right? Beep, pop, boop, pop, pop. You added some solute particles, and they are, again, forming interactions with the water molecules and holding on to them and saying, hey man, don't leave me, don't leave me. So in order to break that attraction between these solute particles and the water or the solvent, the temperature's got to get even higher. So the more stuff that we add to it, the boiling point temperature goes up. So freezing point depression, normally freezing occurs like this. You have these particles kind of moving all around past each other, not in any organized way. They're just kind of flowing, they're doing their thing. And then you cool them down enough, and they start to slow down, and they start to be attracted to each other, and they form a nice crystal structure. It's nice and organized. Now what happens is, when you add solute particles in there, solute particles are kind of messing things up, right? They're like, hey, we have some attraction between us and you guys. Oh wait, you're gonna get rid of us and you're gonna get nice and neat. I don't think so. Mwahahaha. Right? So they're getting in the way. They're blocking things from getting nice and neat. They're saying, I don't think so. You're gonna have to get even colder than you normally would in order to freeze and get nice and organized. So as you put in more stuff, the freezing point decreases. So what? Who cares? Mr. Donahue, this is dumb. I hate this. It's stupid. I don't get it. All right, well, first off, let's talk about antifreeze. Antifreeze uses colligative properties, and it prevents freezing. Hence, antifreeze. So you use antifreeze in your car because your engine gets really, really hot, turns out. There's explosion going on inside of it a bunch of times a second, and it gets really, really hot. So you got to cool it down. So you have coolant that surrounds the engine, and it goes to the radiator, which radiates off the heat and cools it down and sends the cool stuff back to the hot engine to cool it down. Well, if this stuff froze in winter and it froze, remember that water expands when it freezes. So if this water inside froze, well, it would expand and it would break your engine and it would not be good. That's why you need antifreeze, so that the water doesn't freeze, expand, and ruin your vehicle. And then there's also the all-important salt to melt ice. You know, if you got the roadways and you got a car, right? You're driving along in your automobile, right? And, you know, you don't want there to be ice on the road, so you sprinkle some salt on it, and then the freezing point drops. And then it's like, hey, I'm not cold enough to be frozen anymore. Now I'm liquid, I'm melted, and I'll get off the roadway so you don't slip and, I don't know, hit somebody. That'd be bad. All right, so let's do a little critical analysis. So which will have a greater effect, NaCl or Na3PO4? Remember, it has to do with how much stuff, how many particles are going to be in solution. So we got NaCl. Well, that's going to break up into two things. It's going to break up into Na plus and a Cl minus versus Na3PO4. Remember, that's going to break up into 3 Nas and 1 PO4. So it's going to break up into 4 particles. So which one's going to have a greater effect? The Na3PO4, because it has 4 particles instead of 2. It has more. Now, NH4NO3. Don't make the silly mistake of being like, oh, that's a bunch. No, remember NH4 is just one polyatomic ion, so you'll get 1 particle from that. And the same thing with the NO3. It's a polyatomic ion, so the NH4 is going to separate from the NO3, but it's going to stay NH4, and the NO3 is going to stay NO3. So again, you're only going to get 2 particles. Whereas a CaCl2, well, you're going to get 1 calcium ion, and you're going to get 2 chloride ions. So you get 3 particles, which would mean that this one, calcium chloride, would have the greater effect. Which of the following 1 molal aqueous solutions? Now, molal is a concentration. You don't have to really worry so much about it. Just know that it's measuring how much stuff is in there. So which of the following 1 molal aqueous solutions will have the highest boiling point? So I usually draw a thermometer to help me figure out these things, right? So I got boiling point up here and I got freezing point down here. And as I add more stuff, the freezing point drops and the boiling point goes up. So if I'm asking for the highest boiling point, do I want the most stuff or the least stuff? I want the most stuff because the boiling point goes up the more I dissolve stuff into it. So highest wants the most. So let's figure it out. NaCl is going to break up into 2 particles. C6H12O6, well, I know that this is a covalent molecule because it's only nonmetals. Right? That should be an N, nonmetals only. So it's covalent, which means it's a non-electrolyte, which means it's going to stick together and just stay as 1 particle. K3PO4, oh hey look, PO4, it's a polyatomic ion. I also realize that it's just nonmetals and they're going to stick together. So I'm going to get 1 PO4 and I'm going to get 3 Ks, so I'm going to have 4 total. All right, CuNO3, 2. The NO3s are going to stick together, but I got 2 of them. So I get 1 copper, 2 NO3s. I'm going to have 3 particles. All right, so which one has the highest boiling point? The one with the most stuff breaks up into 4 particles is going to be K3PO4. Which of the following 1 mole aqueous solutions will have the lowest boiling point? All right, well, let me think. Lowest boiling point. Again, I like to draw the thermometer because it helps me visualize what's going on. I got boiling point and I got freezing point. More stuff, freezing point gets lower. More stuff, boiling point gets higher. So if I want the lowest boiling point, I want the one that didn't go up as much. So I want the least number of particles. And hey, wouldn't you know it, it's the same stuff as before. I got 2, 1, 4, and 3. Which one is going to give me the least particles? The C6H12O6, the sugar. Which of the following 1 mole aqueous solutions will have the lowest freezing point? So again, I like to draw the thermometer. You go, all right, boiling point, freezing point. Freezing point drops, boiling point goes up. All right, lowest freezing point means, all right, I went down the most, which means the most stuff. So again, got 2 particles, 1 particles, 4, and 3. So which one's going to have the lowest freezing point? K3PO4. Which of the following aqueous solutions will have the highest freezing point? So let me draw my thermometer again. Boiling point, freezing point. We're looking at freezing point. The more stuff I add, the freezing point goes down. So I'm looking for the most amount of stuff in solution. All right, well, I have 500 grams of solute per 1,000 grams of solution. That's like, it simplifies to kind of 1/2 grams per grams. 1,000 grams in 500 grams of solvent. So that's kind of like 2/1 grams per grams is what it would simplify to. 500 grams and 500 grams, that'd be 1/1. And 1,000 grams over 1,000 grams, that again would be 1/1. So which one of these things would have the highest freezing point? All right. Highest freezing point means change the least. So I want the least amount of stuff. The lowest concentration. Well, let's see. I got 2. That's the most. I got 1. And then I got 1/2 over here. So A would be the best answer. It's the least concentrated amount of stuff. Well, I hope you found that helpful. And I'll see you in class. Bring questions.